Hi everyone, and welcome back to EasyEDA. In our last lesson, we wrapped up the motion control functions. So in this session, we're going to move on and complete the rest of the feature functions, things like Wi-Fi setup, weather display, clock functions, ADC readings, and more. Alright, let's officially dive into today's topic, writing the rest of our functions. The lesson is broken into 5 main parts. First, getting weather data. Second, Wi-Fi configuration. Third, ADC calculations. Finally, we'll wrap up with a quick summary. Let's start with the first part, fetching weather information. For this, we're using Sensitive Weather API. Now, why do we use it like this? If you're curious, you can go check out the API documentation. It explains the request structure and logic in detail. Let's open up VS Code and start coding. By now, you should have already completed the motion control section, so we'll just continue from there and work on the weather section. Earlier, we defined a variable to initialize the weather feature. Let's check if you already declared the Boolean variable called weather. Yep, here it is. The variable ensues we only send one weather request each time when we open the interface, prevent it repeating API calls. This helps save power and bandwidth. So let's write a condition. If it's the first time loading the screen, then we send a network request. Step 1 obviously is to check the Wi-Fi status, whether we're connected. We do that by checking if Wi-Fi.status equal to WL-connected. Next, we create an HTTP client. We're using HTTP here, not HTTPS, just plain HTTP. Then we send out our API request. The request link or URL is already defined earlier in the code. Let's remake the variable to something clearer, like URL, or avoid confusion with your API token. Remember, this URI is just an access path, it's not a token. The token is something you get from sensitive official site after you register and log in. Let's build the full API request URL by appending a few key parameters like location, language zh-hands, unit equals to C, and start 0, days 1. All of these parameters are clearly explained in the documentation. Next, we send the GET request and check the HTTP status code. If HTTP code is greater than 0, that means the request was successful. Then we define a string to store the response value from the API. You can print it out to the serial monitor to check whether the returned JSON format matches what the docs describe. Now let's parse the JSON. We're using the Arduino JSON library here. First, we create a dynamic JSON document with a size of 1024 bytes. Watch the spelling, it's payload, not payload. The word payload means the data you get back from the API. We parse the data using deserialization, doc payload. Then we extract the values we need, temperature 2, the high temperature, humidity 2 for humidity, weather 2 for weather description. I've added a 2 to each name to avoid name collisions with any global variables we defined earlier. Now assign these local values to your global variables so we can use them throughout the program without sending them new requests anytime. We can print the temperature and humidity again via serial to double check if everything is working. Once everything's done, don't forget to set the init flag to true. Just tell the system we've already loaded the weather data. If the HTTP status code is less than 0, the request failed. In that case, you can use serial printf to print an error message like error on sending request. You can even call http.error to string HTTP code to get more specific errors, like DNS issues, connection problems, or the server didn't respond. Like finally, don't forget to close the HTTP client and release resources. If it fails at http.begin, you can display an error message like http begin failed. Now that we've got the weather data, let's show the corresponding icons on the screen. For example, if the weather status is something like cloudy or overcast, we display a related image. Start a new page with uag2.nextPage and set the font with uag2.setFont. You can use the default font or even import a Chinese font library to uag2 if you want to display Chinese character directly. Next, display a 64 by 64 icon at position. Make sure the icon variable name matches the one in your image.cpp file. If you call it cloudy icon, then write cloudy icon here. Then display a temperature string. First, consonate something like temperature in Celsius and convert it into CHAR because DRAOSTR bracket only accepts C-style strings. Put the temperature at 6420, humidity at 6430, and so on. Just swap in the right values and add a percentage sign. Later, you can add more else if block in to handle other conditions like sunny, light rain, heavy rain, thunderstorm, etc. No need to explain each one, just copy paste and change the conditions in the icons. Once everything compiles without errors, you're good to go. That wraps up the weather display feature. Next up, Wi-Fi configuration, loading and using Wi-Fi settings. We actually did part of this earlier during the connect function. Let's scroll back up. Yep, right here. We've saved the SSID, password, city name, and API key into the SPIFF's file system. We're going to save all the info from the web form, Wi-Fi name, password, city, and API key into a JSON file, and then write it to SPIFFs. Don't worry about the field name inside the JSON. They're just keys, they won't conflict with your variable names. Remember to end each line with a semicolon. If there are no compile errors, then say the operation worked. Now let's load those settings from the file system and automatically connect to Wi-Fi. How do we do that? Same logic. Start spiffs with spiffs.begin, then open the file using spiffs.open. To make sure you use a comma, not a period. Check if the file opens successfully with if file. Now parse it with Arduino JSON again. Declare a dynamic JSON document doc and run deserialization JSON doc file. If there is no error, we can extract the fields SSID equal to doc and similarity for password, city, API, etc. You can store them into local variables and then copy them to global ones like CPP, city name equals to city, weather API equals to API, or just assign them directly to global vars if you want. Either way works. At this point, you got your city name and API token ready. So what do we do with the Wi-Fi name and password? Obviously connect your Wi-Fi. Set a timeout, say 10 seconds. Every 500 milliseconds, check if Wi-Fi is connected. If connection fails, call handle-wifi.configure to switch into web configuration mode. So when you first power on your robot and there's no saved Wi-Fi config, it will automatically go into web config mode. Notice we're not using a blocking loop to wait for Wi-Fi. That's intentional because your robot might be used in places without Wi-Fi. Instead, we just check Wi-Fi status periodically, none blocking. Once connected, print a message to confirm connection success. Then start the NTP servers to get the current time. Finally, close the config file using file.close to release resources. If you got compile errors like mismatched parentheses, just fix them and recompile. Once that's done, Wi-Fi config is complete. Let's move on to ADC voltage reading. Now in the ADC section, start by defining an integer ADC value equals to 0 to hone the sum of examples. The run for a loop to make multiple examples sets 10 times, average the result. Convert this average to voltage, assume your ADC is a 10-bit and your reference voltage is 3.3 volt. Then estimate the battery level. You should have already defined the voltage range, set 4.2 volt max and 3.3 volt min. If the voltage is smaller to 3.3 volt, battery level should be equal to 0 degrees. If the battery voltage is bigger than 4.2 volt, battery level is equal to 100 degrees or 100%. For values in between, you can do a simple linear interpolation or skip if you want. Now if you got a percentage, you can show the OLED or web interface. Alright, let's do a quick recap about what we covered in this session. Weather API, use sensitive API to fetch current weather, temperature, humidity, and display it with matching icons. Wi-Fi config, save settings for the web page to CIFS and read them back to AutoConnect. ADC voltage reading, measure battery voltage and convert it into percentage. You can keep adding stuff, voice control, obstacle avoidance, whatever you want. As long as you're willing to write the code, your robot can do it. Alright, that's it for the lesson. Thank you for watching.